Good morning, guys. Is the audio clear? No
Yes, sir.
disturbance?
Yes,
So there are two options from my side for you guys because we went all the subjects throughout the subject in a slower pace. Now we are facing a difficulty in the sense we have around 4 to 5 classes and we need to finish whole of a new model. For that, I give you two options. Number one is engaging a special class that is at 5:30 or 6 o'clock in the evening for about 30 to 40 minutes and for 3 to 4 days. That is the one option. And second option is that speeding up in the present classes itself, in the sense if I have a class for 1 hour, so I would just go on explaining the things and fill the content for the 1 hour. So the option is left to you, and based on your response, we will decide. Got the two options, right? Number one, taking the special class in the evening from 5:30 to 6 or around 30 to 40 minutes for 3 to 4 days. And the second option is speeding up the content within the scheduled class itself. So which one you choose, just give me a response in the chat box. Okay. I need a response from everyone. Okay, sure. That's also true. I need response from everyone. Okay. Okay then. So without any further ado, we shall start the today's content. We shall try to solve a few problems on second law of thermodynamics as we have solved in the previous class for today's session. Okay. Kindly concentrate, guys. Do not take it as a burden. Okay. Yes. Are you able to see the screen now?
yes, sir.
So from now on, so if you finish the second law of thermodynamics, then the content associated with the basic thermodynamics will come to an end. Okay. So from the module number 3, that is the next module. So whatever you study will be based on the heat transfer. I hope for all of you guys and I think for everyone, heat transfer concepts are more easier when compared to the basic thermodynamics concepts. Even the basic, I'm not saying that basic thermodynamics concepts are tough and tough to understand. I don't say that, but comparatively, when you take a comparative study, the heat transfer concepts are more easy when compared to the basic thermodynamics concept. By now, how was the basic thermodynamics for you now? Did you understand all the concepts? Whether you feel difficult for the subject?
Understood, sir.
Understood, right? So even the heat transfer, that is the module number 3 talks about the basic introduction about the heat transfer, which is very, very easy, which gives a gist of all the three ways, that is conduction, convection, and radiation. And module number 4, you will study about the conduction, and module number 5, you study about the radiation. So you can skip the convection part over there. So just to do not overburden you with all the concepts, I can skip the convection part from both module number 4 and module number 5. That will not affect your syllabus anyhow. So if you could plan in such a way that module number 3, if you go for heat transfer, then there will have all the three heat transfers, that is conduction, convection, and radiation. Module number 4, you will go with the conduction, so in-depth concepts related to the conduction. And in module number 5, you study about the radiation, skipping the convection. This plan is okay with every. Yeah. Yes, man. Karthik, Shabit, Namita,
I think your voice was
Ashmita.
breaking.
Yes, sir.
Yes, sir.
Connected my Bluetooth headset. Okay. Change. Just check for it now, whether it is clear.
Yes, sir, it is clear.
Yes, sir. Now it is clear.
Thank you. Okay, so we shall start with second law of thermodynamics problems. Okay, we have solved a couple of them in the previous class. We'll try to look into some of them here also. Okay, fine. So in this particular problem, which is the third problem which I'm going to solve, a heat engine in a cycle, kindly concentrate, guys. Concentrate in order to understand.
Sir,
Sir,
actually, your voice is breaking, sir.
Okay, there might be issue with the internet. I'll just check this out. Okay.
Okay, sir.
Yes, guys, just check now whether it is clear.
Yes, sir.
Okay, so please do interrupt me when the voice is not clear. Okay.
Sure, sir.
Yeah. Yes. So we were discussing few of the problems. So third problem now. Let us read the question. I told it I may be not too much interactive with you, but please do engage in the class. This is very, very important. Now understand the concepts, okay? Fine. Now, a heat engine in a cycle delivering work equal to 22 into 10 to the power of 3 Newton meters. So this is the amount of work which is being delivered. So I can just write it W equal to 22 into 10 to the power of 3 Newton per meter, which is the work developed here. Okay. Next. And absorbs 95 kilojoules of heat. So this is 25 and let 22 into 10 to the power of 3 Newton meters. Let me write here. And absorbs 95 kilojoules. Absorbs in the sense whether it is Q1 or Q2. With
Q1,
respect to
sir.
heat engine. So Q1
Q1.
is
Q1.
Q1 is given as 95 kilojoules of heat. Determine the efficiency of the heat engine. So you have to find and heat transfer from the working to find out. As simple as that. Okay. So W is given by what? Q1 minus Q2. You know the value of W, which is here. You know the value of Q1, which is here. You can calculate the value of Q2. And once you've calculated the value of Q2, so whatever the values I have calculated, I'll be writing in the green. So Q2 is equals to how much you have calculated it as 73 now. Now you have to calculate your thermal efficiency. Thermal efficiency is nothing but what? The work output divided by the heat input. So WHE divided by heat input in the sense it is Q1. So WHE you have already given in the form of the given things. So W is given, Q1 you already know, you can calculate thermal efficiency. So simple problem. Any doubts in this? Any doubts?
No, sir.
Understood the problem?
Yeah.
Okay. Shall move to the next one. Okay. A heat engine working at a rate of 105 kilowatt. So 105 kilowatt has an efficiency of 22%. Determine the quantity of heat received. Determine the quantity of heat received in the sense which I should received and transferred from the working fluid and Q here. So it is a heat engine. So first let me draw a heat engine. It will receive its temperature source and there is a sink T2. So it receives Q1 amount of heat. It ejects Q2 amount of heat. Thereby, the difference between these two will be given as the work output. That is Q1 minus Q2. So what are the things given here in this problem? Yes.
Work
What are
output.
work output is given. So work output is how much?
105 kilowatt.
So it is 105 kilowatt and efficiency is also given, which is 22%. Okay. You know that efficiency of a heat engine is nothing but here, the work output divided by the heat supplied. Work output is known, Q1 is unknown, but you know the efficiency. Thereby, you can calculate what is the value of Q1, right? So Q1 you can calculate as Q1 is equals to 477.27 kilojoules per second. This is the calculated value. So since you know the value of Q1, since you know what is the work output, easily you can calculate what is the value of Q2, since these two values are known, is it? So same thing, W is equals to Q1 minus Q2. W is calculated, okay? Q1 is known, and you can calculate what is Q2. Thereby, you calculate the value of what is the quantity of heat received and what is the quantity of heat transferred from the working fluid. Any doubts in this problem again?
No, sir.
Okay. Kindly concentrate, and in the meantime, if you feel bored, if you feel stressed, just give me a then start. Everyone to just listen. That's it. Okay. The fifth problem, guys. A reversed heat engine absorbs 220 kilojoules of heat from a lower temperature region and has a mechanical output of 90 kilojoules. Determine the quantity of heat transferred to a higher temperature region. Also, determine the COP of the reversed engine when working as a refrigerator and as a heat pump. So this is a very good question here. The first, he talks about what? He talks about the heat engine. If a heat engine is reversed, what happens? It becomes a refrigerator. If you could observe in the last few problems, the heat flow, the heat flow was in direction because yes or no. Now, in case of a heat pump, which is this, or in case of a refrigerator, which is this, the heat flow will be from the lower temperature region to a higher temperature region like this. In order to do so, I should work on the system according to the Clausius statement, which is this. Getting the things, guys?
Yes, sir. Clear.
Now, now, um, so what he has given in the problem, the reversed heat engine. So reversed heat engine is nothing but the heat pump or a refrigerator. Keep this in mind. A reversed heat engine is what? The heat engine in a reverse fashion. So if you reverse a heat engine, what happens? It either, if there is a heat engine, if you reverse it, what happens? It either becomes a heat pump or it becomes a refrigerator based on what you want, what is your intention. So based on that, it will turn into a heat pump or a refrigerator. Okay. So he asked us to analyze in both the sense, both the aspects. We shall do it. Okay. The heat reversed heat engine absorbs 220 kilojoules of heat. So what is this 220 given? What is this
Sir, from
Q20?
the Q2.
Excellent. So it is the value of Q2 which is given, which is 220, which is same for both the cases. Okay. Now, from a lower temperature region. So this is your lower temperature region. That is what you have known. Now, the region, okay, and has a mechanical input of 90 kilojoules. So what is this parameter given? I think it is the value of W, is it? So the
Yes, sir.
mechanical, it has 90 kilojoules of mechanical input. Okay. So since the value of input and the value of Q2 is given, I think you can calculate the value of Q1 directly, where W is given by Q1 minus Q2. So Q1 is W plus Q2 here. Yeah, here. So just add these two. Since C, it is the nature of flow, is it? This is W, this is Q2. You have to add these two so that you get the value of Q1. As simple as that. Flow dynamics. Okay. So it is 90 plus 220, it is 310. So the value of Q1 joules. It is same for interpretation is different. By analyzing this problem, you will be in a position to understand what is the word COP. So W is 90 here. See, if you observe these two figures, the number one, and number 2. So here it is a heat pump, which is number 1, and the refrigerator, which is number 2. All the things are same. All the things are same. But the thing is, the area where you concentrate differs. So how do you calculate a COP of a refrigerator? First of all, how do you calculate a COP? Just a COP. How do you calculate it? Would you
Desired
able to
effect by
recall?
net work done.
Excellent, excellent, Shabit. This desired effect. Sorry for the harsh voice which is coming out from my mouth. I'm not feeling well since last night. A little bit of cold. Okay. Desired effect divided by work input. This is the thing. Now, the desired effect in case of refrigerator as well as the heat pump varies. So, what could be my desired effect? What could be my desired effect in case of a heat pump? What is my desired effect? What do I desire for?
Heating.
So I desire a heating. So my desired effect could be the value of Q1. So therefore, the COP of a refrigerator is equal to Q2, which is the desired effect. And the work input value is W. So thereby, Q2 is what? It is 310 divided by, sorry, it's Q1, right? Desired effect is Q1. Yes, it's Q1. I've just overwritten it. So Q1 divided by W. So Q1 is what? 310 divided by W is 90. It's the wrong, yes. That is equal to 310 divided by 90 is what? 3.14. So that is COP of a refrigerator. Okay. Similarly, if you want to calculate the COP of a heat pump, I think I'm going wrong somewhere.
So is it reversed?
Yes, it is reversed. Just a minute. Take care of all this. It's correct. All the things are correct. See, let us try to analyze the refrigerator one. Okay. For COP of a refrigerator, it is nothing but the desired effect. Okay. Divided by the work input. Okay. Now, in this COP of a refrigerator, which is this, I was looking into heat pump initially, is it? I was looking into heat pump. That's why I was called wrong. So COP of refrigerator, in the sense I have to look for the refrigerator here. In the refrigerator, what is my desired effect? Heating or cooling?
Cooling Q2.
So cooling is my desired effect. That's why I need to take the value of Q2 as my desired effect. So that is the Q2 divided by W. So what is the value of Q2? It's 220 divided by work input is 90. So thereby COP of a refrigerator is what? Whatever here is the value here, it is 2.44. Similarly, if I want to analyze the heat pump now, which is this particular thing here, the same thing. The COP of a heat pump I must calculate, which is again a desired effect, okay, divided by the work input. So in this case, in a heat pump, your desired effect could be what? Heating. So if you want heating, your desired effect is Q1 here. So it is Q1 divided by the work input, which is W. That is Q1 is how much? Q1 is 310 divided by work input is 90. So this value accounts to be 3.44. So COP of a heat pump is 3.44. So if you observe these two values, And we have derived given an expression stating that COP of a refrigerator is equals to 1 plus COP of a heat pump. Yes or no? We have derived this.
Yes, sir.
So that particular thing satisfies for this also. So 2.44 plus 1 is 3.44. Any doubts in this particular problem? Should I have that
No,
problem?
sir.
Clear?
Yes.
Okay. Now, let us move to the next one. And this problem is not required for you because it's complex. I will just, if you are interested, I will just share gist of it. So this is a beautiful problem where you will try to analyze. So where in this particular problem, what happens is your heat engine, your heat engine, your heat engine will develop certain amount of work, is it? That is why your heat engine is designed for. Your heat engine will develop certain amount of work, and your refrigerator needs some amount of work to be acted on it. Some amount of work you have to work on it so that your refrigerator work. What if I combine these two like this? If I combine these two, that means whatever the work output you're getting from the heat engine, if I just use the same work output to run a refrigerator, and how to analyze such systems is the beauty of this problem. Okay, it's very good, but not required for you guys. Okay. Now, problem number 7. In the reversed heat engine, the work done on the engine is 75. So reversed heat engine in the sense it could be a heat pump, or it could be a refrigerator. I think it has the same thing previously, but little bit of parameters might be shuffled. Reversed heat engine, this is the heat engine, and the work done is how much? 225 or 75. It's 75. Now, heat transfer from the lower temperature region to engine is 225. So Q2 value is 225 from a lower temperature region. Determine the heat transfer to a higher temperature region, which is Q1 is questioned, and the coefficient of performance as a refrigerator and as a heat. I think it is very much similar to the previous problem. Is that? Are you able to find any difference from the previous problem for this particular problem here?
No, sir.
It's exactly similar, I guess.
Yes.
Let us move to the next one. All these concepts are not required. Which are not required, I have just marked them. Okay, this is also not required. Yes, this is a good problem. We should try to solve this again. Now, look here. When 50 kilowatt of power is supplied to a heat pump. So he has given. Okay. So 50 kilowatt of power is supplied to a heat pump, he says. That means he has given the value of what? He has given the value of work input to a heat pump. Its coefficient of performance is 5. Excellent. So he has given the COP of the heat pump as 5. Fine. Determine the rate of heat transfers to and from the working fluid. Okay, here the rate of heat transfers to and from, both you have to find. That means you have to find what is the value of Q1, and even you have to find what is the value of Q2. So that is the question given. Okay. And the second case, in the second case, he says, if the heat pump is used to heat a water in a heat exchanger, while its temperature increases from 50 degrees to 75 degrees, okay, in a flowing through a heat pump. Determine the mass flow rate of heating water. Okay, this is excellent, and this is an extra stuff. Hopefully, probably this type of questions will not be asked, but yet we will cover this. This is not a big deal. Okay, so W value is given in this problem. COP is being given. So again, it is the desired effect divided by work input. Okay, what is the desired effect in case of a heat pump here? Anyone? What is the desired effect in case of a heat pump? 1 or 2? What is the desired effect?
Q1.
Q1 is a desired effect. So Q1 divided by work input, that is the COP of the heat pump. I think COP of the heat pump is given, which is 5. Q1 is given is not given, and W is given, so which is 50. I think you can calculate the value of Q1 here. Simple, right? So W is nothing but Q1 minus Q2. So from this, W would be known. W anyhow it is given. Q1 you have just calculated recently. So there is no problem in calculating the value of Q2. Is it? So there hence your syllabus. Actually, they have to ask within this margin itself. But for the extra knowledge, we shall try to solve the second bit also. So here, what he says is, yes, if a heat pump is used to heat a water in a heat exchanger. So see, what I will be doing here is, this is there, right? Where you are pumping the heat in. So for this pumping the heat in this particular segment, I will be incorporating my water heater like this. So water heater will be just incorporating. So the temperature entering this particular water heater, he has given it as 50 degrees Celsius, and the temperature which is gained, that is the exit temperature, is being given as 70 degrees Celsius. 75, sorry. 75 degrees Celsius. Now, he is asking us to calculate the mass flow rate of heated water by neglecting the water velocity. Okay, fine. So now I should calculate with what speed the water will be moving. Got the question, everyone? Understood the question, first of all?
Yes, sir.
So for this type of questions, there is a standard formula which is known as MCP into delta T. This will get to know in depth of thermodynamics, but as of now, we just remember the heat transfer from the water to any other things can be calculated as Q is equals to MCP delta T. Hope you have come across such formulas in the second few times, but just do remember this formulas. It might help you in any of this concepts. Q is equals to MCP delta T. So Q is nothing but the value of Q1, which is providing. So Q1 amount of heat you are providing into it, right? That is the amount of heat which is going in. Yes or no? That is tackling on the water. So Q1. So that is, okay, Q1 is equals to M. M, you have to find out just the mass flow rate into the value of CP. So the value of CP in the very beginning classes, that is around the module 1, when I was talking, I asked you to remember the values of CP, CV, and R for both air and water. Yes or no? Very long ago, I have just asked you to just remember the values of CP, CV, and even gamma for both air and water. So that this is how it will come into help. Okay, always have this values in your back of the notes, so that it should be in your mind itself, so that if any such problems gets tackled, you can answer it straight away.
1
Okay, do not
kilojoule per kg for air.
It is 4.18 kilojoules per kg. That is the value of CP. So they have just used it. So here they have just used it here. So T2 value was 75 and T1 value was 50 as indicated here. Thereby, you can calculate what is your mass flow rate. Simple problem, but a new concept. Understood? Understood this problem? Any doubts here? Any doubts?
No, sir.
No, sir.
Okay. Fine. This is required. Okay, you can try this. This is again the same thing where you need to find the values of T1 and T2. Some of the constraints should be given. According to that, you have to find the value of T1 and T2. This will be provided to you in the form of a notes. I think I thought of giving this an assignment, but no time, no this thing. So just try this. If you face any difficulty, you can just let me know because I want you to try something. Okay. And there is a last concept, which is this thing. See, okay. Just concentrate on the concept. Don't go with the derivation. It is a huge derivation, not required for you guys. Just concentrate on the concept. So this concept says like this. So I have an engine number 1, which is operating between T1 and T2. Okay. I have engine 2, which is operating between T2 and T3. That means what I have done is I have coupled this thermal reservoir. What I have done, I have coupled this particular thermal reservoir between engine 1 and engine 2. Got it? So this particular thing is known as an intermediate reservoir. What is this known? It is known as intermediate thermal reservoir. Okay, so this is the intermediate thermal reservoir, which acts as a source for engine number 2, but it acts as a sink for engine number 1. So that is known as the intermediate thermal reservoir. There are certain conditions, guys. Conditions in the sense, what if this particular engine and this particular engine, which is E1 and E2, what if these both engines will give the same work output? Then what will be this temperature? This is the first thing. Got it? What was my question? See, if engine 1 and engine 2, both of them gave the same work output, then what will be the value of T2? This is my first question. Second question is, what if the efficiency of engine 1 is equal to the efficiency of engine 2? Okay? The efficiency of engine 1, if it is equal to the efficiency of engine 2, then what will be my intermediate temperature? This is my question number 2. The answers for these two questions are here. Okay? So T2, which is the intermediate temperature, will be a arithmetic mean in the sense T1 plus T3 by 2. What is T1? T1 is upper temperature. T2 is what? T2 is a lower temperature. Okay, I should rub all this. T1 is the upper temperature and T2 is the lower temperature. Okay, so if the work output of these two engines is same, here it is. For engines with same work output. Okay, if the work output of engine 1 is equal to the work output of engine 2, then your intermediate reservoir temperature would be the arithmetic mean, that is average of these two, T1 plus T3 divided by 2. Similarly, what if that is the answer for the second question where I said, if both the engines 1 and engines 2 have a same thermal efficiency, then it will be a geometric mean which is equal to the square root of T1 and T3. The intermediate temperature would be a geometric mean which is equal to the square root of T1 and T3 if both the engines has the same efficiency. Clear, guys, with these two concepts? Any doubts here?
No, sir.
Yes, sir.
Understood, right? So just we shall recall some of this and interact with each other again. Ashwita? Ashwita?
Yes, sir.
how to calculate my intermediate reservoir temperature if both of my engines have a same work output?
Take the arithmetic, the T1 plus T3 by
By
2.
2. It is nothing but the arithmetic mean of the other two temperatures, which is T1 and T3. So T1 plus T3 by 2, there it can calculate. Yes. Next, Namita.
Yes, sir.
So how do I calculate my intermediate temperature if both of my engines have the same efficiency?
Geometric mean T2 equal to root of T1 by T3. Sorry, T1 into T3.
Everyone clear with these two concepts? Any doubts here?
No,
Any?
sir.
Okay.
No, sir.
Okay. So there is a derivation. How do you get into this? That is not required. So I have just marked in this particular PDF where you have to remember only the things which I have highlighted here. Okay, I have said remember only this. Remember only this. That's enough. Okay, no need of the derivation of that. Okay, based on that, we will be having a couple of problems like this here. Huh? Can you able to read it? Karthik, can you just read this out?
Yes, sir.
Hmm.
A source at a temperature T1K supplies heat to a reversible heat engine which rejects heat to a low temperature sink at 720 K.
Okay.
The sink at 720
Hmm.
Kelvin acts as a source for the second reversible engine which rejects heat to the cool reservoir at 280 K.
Okay. So T1 is
Determine determine
determined.
T1
Hmm.
T1.
Mhm.
The condition is for equal thermal efficiency of two engines.
Mhm.
Second condition is when two engines deliver the same amount of work.
Okay. Any difficulty in solving this after knowing the concepts?
No, sir. It's clear.
Hmm? I want answers from everyone. Man. Any difficulty in solving this? It's just for the same efficiency. T2 would be equal to what? The square root of T1 and the T3. And for the same work output, the T2 will be the arithmetic mean, that is T1 plus T3 divided by 2. Based on these two equations, he has given the value of T2, he has given the value of T3. You must calculate what is the value of T1. So there are two equations, one unknown easily can be solved using the mathematics. Okay. Similarly, the not necessarily be such questions. Even such questions can also be asked. I will just read it out. I know my handwriting is worse. Two Carnot engines work in series between a source and a sink temperature of, this is 550 Kelvin and 350 Kelvin. That means he has given the value of T1, he has given the value of T3 here. If both the engines develop equal work, determine the intermediate temperature. So this was asked for 8 marks for the mechanical department, but it can be asked for 6 marks for you without any sort of derivation. Okay, I have seen your question papers, nowhere it has asked for the derivation. So T1 he has given, T3 he has given, and if both the engines have the same efficiency, find the intermediate temperature. So T2 is equals to, again use the same formulas, T1 plus T3 divided by 2. This is for the same work output, and T2 is equal to square root of T1 and T3, which is for the same efficiency. So use these two equations to get the value of T2, thereby you'll get the mass given. Any doubts, guys?
No, sir.
No, sir.
So whether all the problems were clear, was I in a rush?
No, sir.
No,
Clear.
clear.
Yes, sir. Yeah.
So here it ends the second law of thermodynamics and the module number 2 and the concepts of basic thermodynamics. So from the next class, we'll be starting a newer concepts, totally different stories about the heat transfers, about convection, and radiation. Okay, that is very, very interesting. We shall start it from the next class. Okay, so first give your attendance. Okay, give your attendance, guys. Abdul Rahman,
Present, sir.
Abhinav, Adarsh,
Present, sir.
Ahmed Reza,
Yes, sir.
Shayar Kotian, Amitesh Hari,
Present, sir.
Amrit,
Present, sir.
Ashwin KV,
Present, sir.
Huh?
Present.
Present, sir.
Shimpanski,
Present, sir.
Noy,
Present, sir.
Hard,
Yes, sir.
Faisal, Gaurav,
Present, sir.
Gautam HS,
Yes, sir.
yes,
Yes, sir.
okay, that's fine. Well,
Present, sir.
M. Karthik is there, Fazil, Muhammad Siha,
Present, sir.
Tausif Ali,
Present, sir.
Nuwas, N. Suraj,
Present, sir.
Nafa,
Present, sir.
Krishnamita,
Present, sir.
Nafa, have you played the full piece, Nafa Abdul Rahman? Nandish,
Present, sir.
Nathan,
Present, sir.
Niharika, Nishchit,
Present, sir.
St. George, Omkar,
Sir, Nedim Rasan.
Satish Suvarna, Karthik,
Present, sir.
Rajat Rai,
Present, sir.
Rakshan K,
Present, sir.
Ramdas,
Present, sir.
Sanjit,
Present, sir.
Sabat,
Present, sir.
Sagar Acharya,
Present, sir.
Shahzad Abdullah,
Present, sir.
PC, Shetty Sujay,
Sir, present, sir.
Shetty Tejas,
Shashank.
Present, sir.
okay, Shashank Kumar,
Yes, sir. I'm
Right.
betting.
Shravan Kumar,
Present, sir.
Yes, sir.
Shetty Tejas.
is Sriraj, Saurabha,
Present, sir.
next is Sumant, Varun, Vigneshwara, Amit Sangoi,
Present, sir.
Nilesh Markal,
Present, sir.
next spiritual Heckaday,
Present, sir.
okay, and Sandesh, Rachan, Rohan,
Present, sir.
Varun, Dashvi, Mohammed Amin,
Present,
Sir,
sir.
others.
Numan.
Present, sir.
Okay, man. So I have heard that few of you guys, Vigneshwara, Suman, Saurabh, Benoy, Gautam, and Ramdas, have been selected for KPIT Sparkle, is it? Congratulations for you, man. You do well. Okay. And from the next class, Adarsh, I have marked you. Adarsh Panchal, I have marked you. From the next class, we shall start the heat transfer concepts entirely in lifting. Okay. Till then, take care. Have a nice day.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Internet issues. Could you please upload the recordings to the Google Classroom? I will do it. I will do it.
Excuse me, sir.